Hey guys, so let's talk about conservation of momentum. Let's work out an example. So in this example, there is a particle coming in. Okay, let's draw it over here. So there's a particle moving towards the north. And there's a particle moving towards east. Okay, let's say that their masses are, so let's say that this is 2 kilograms, and this is, it's moving with velocity of 3 meters per second. And let's say that this guy has a mass of 3 kilograms, and it is moving with a velocity of 2 meters per second. Okay. Now, what happens is that they collide. We set up the problem in such a way that they collide at the origin, okay, and then they both move as a blob in some direction over here. So we have to figure out this angle theta and the velocity of this blob. Okay, so we'll use conservation of momentum to figure this one out. So how do we approach this? So it's an easy problem. We can apply conservation of momentum. So the momentum, since the particles are moving along the x-axis and y-axis, right? So momentum has to be conserved in both the x and y directions. So P final x has to be equal to P initial x, right? And P final y has to be equal to P initial y, right? So in other words, like the conservation of momentum is a vector equation, right? So it means that you have to make sure that momentum is conserved separately in the x direction and in the y direction, right? So now, how do we apply conservation of momentum? Now we have to make sure. Now initially, there is this particle. So the total initial momentum is what? So it's basically the vector sum of these two. So initially only this particle has x momentum, right? So finally the x component of this momentum, the final momentum, has to be equal to this initial momentum, right? Because this one is carrying no x momentum, right? And the y momentum, the y component of this final momentum, has to be equal to the momentum of this particle, right? So so as I said, it's an easy problem. If this particle was, for example, moving at an angle, then you have to basically add the y component to this also. But we will discuss extension of this example later. So let's apply conservation of momentum. So for the x direction, we get so initial momentum in the x direction is what? It's this one. It's the product of this. So you get m1 v1 is equal to. So it's the x component of this has a cosine theta, right? The closer angle, the side closer to the angle, has a cosine theta, right? So now so this is, I'm going to write it as P final cosine theta, right? Now this is equal to m1 v1 equal to capital M. Now this mass is the total mass. It's the sum of the mass of this blob is the sum of the masses of the two particles. So that's going to be mvf cosine theta and let's call this equation 1. And in the y direction, we get m2 v2 equals P. Now for the y direction, this momentum, right, is the initial momentum. This is going to be equal to the y component of the final momentum, right? So that's pf sine theta. Okay. So which is equal to, which is equivalent to m2 v2 equals capital M vf sine theta. So that's our equation 2. Now, now we have to solve these two equations. Let's solve them over here. So we can divide the two equations. So let's divide 2 by 1. So 2 divided by 1, what does that give us? So we get, so you have to divide these two. So this comes at the top, so you get M2V2 divided by M1V1 on the left hand side, and the capital M and VF. So the capital M and VF will cancel out, right? Sine theta, MVF cosine theta. So we get tangent theta equals M2V2 over M1V1. Now you can see that the product of M1V1, right? In other words, P1, P initial 1 is just 6 kilograms meters per second, and P initial of particle 2 is also 6 kilograms meters per second. The product is the same, so 2 times 3, this is also 3 times 2, so it's the same product, so we just get 1 over here. So this tells us that theta, tangent inverse of 1 is 45 degrees, so theta is 45 degrees. So that's our angle, that's theta, is 45 degrees, okay? Now, what about the velocity? So you can use any of these two equations to get the velocity. Oops, sorry. Yeah, there you go. So again, M2V2 is equal to M1V1. So they both have the same value. This is 6 kilograms meters per second. This is also 6 kilograms meters per second. So you get theta equals 45 degrees. So, so you can use any of these two equations to get the value of VF. So we can, let's write that over here. So VF is going to be equal to, so let's use VF. Let's use this equation. So we get VF equals M1V1 or capital M, capital M times cosine theta. So you can plug in the values to see, so this is 6 kilograms meters per second, the product of these two. The capital M is 2, it's the sum of these two masses. So capital M is 2 plus 3, so you get 5 kilograms over here, and cosine 45 degrees. So that should give you 1.7 meters per second. So this is it. So it's a fairly simple problem. And I'll talk about a different way of solving this problem. In terms of vectors, right? I'll talk about that in the next video. Thanks for watching. Bye.